Welcome back. So we're going to go back to our shared desktop and continue on with part 2 of this lab practical. So in part 1 we talked about computing the orbitals, the structure, and the electron density of this aniline molecule, doing almost everything through the command line. Now our next step is going to be to compute the electrostatic potential. We're going to use CubeGen again to do that, only this time rather than computing the HOMO and LUMO, I'm going to compute POT equals SCF. POT means the electrostatic potential, SCF means computed from the orbitals. So I'm going to call this aniline electrostatic potential.cube. I type in this command line, I hit enter, CubeGen is running. It's going to take a little longer than it took before because it takes a little extra time to compute that electrostatic potential at every point in this grid. Okay, now once we're done, I'm going to go back into Gauss view and try and visualize these results. I'm going to go to results, file open rather, and I'm going to open my aniline density. So this is the cube file. This is just the information in the cube file. And I could go to results, surfaces, contours, and just look at the surface of all points where the computed electron density equals 0.0004 electrons per cubic Bohr. So that's what it looks like. Again, these are the sorts of things that you can measure in an X-ray crystallography experiment, so these density isosurfaces are things that you could get from an experiment. If I hide that surface and I go to a much larger density cutoff and I generate a new surface, now it looks a lot more compact because this is the surface of higher density. This is the surface of lower density. This is the surface of higher density. So alright, that's all fine. I'm going to delete this high density surface because my next step is going to be to evaluate the electrostatic potential. I'm going to go back to my 001. I'm going to delete this surface as well so I don't get confused. To do this, I need 2 cubes of points. One that's the density, one that's the electrostatic potential. So I'm going to load my second cube of points of the aniline electrostatic potential. Now to visualize this, I'm going to click on the electron density, and I'm going to go to New Mapped Surface, which means the surface is going to be colored by the value from a different cube. I only have one cube there. And so this is what I get. This is the electron density, the surface of points where the electron density equals 0.001 electrons per cubic Bohr, colored where red is negatively charged regions and blue is positively charged regions. And what do we see? Isn't that nice? My cutoff is symmetric, but it doesn't need to be, minus 0.002. Minus 0.05. There we go. That's a nice range. You can tune where the red starts and where the blue starts by modifying what you type into these values. And this is what I see. Take a look. This should make chemical sense. The most negatively charged region of this particular density isosurface, the most negatively charged region is in the middle of the pi system. And then on the outside of the benzene pi system, I have not quite as negatively charged. I have a little more positively charged region on the benzene CH groups, and the most positively charged regions are on the NH groups from the nitrogen. So here's negative charge and here's positive charge. All the things that you would expect chemically about this system, but now we get to compute it and show it in a nice way. So when you look at, for example, an alpha-beta unsaturated ketone, you're going to see that the regions where you'll get nucleophilic attack are going to be slightly positively charged, but they're also going to be, maybe some will be big and puffy and diffuse orbitals, some will be small orbitals, some will have a large contribution from the HOMO, some will have a small contribution from the HOMO. These are things that you'll need to look at and talk through and read about the literature and make sense of. But anyway, that is how you compute this. The last thing that I'll show you, how would I save this image? I could do save image file if I wanted to save this picture. Or, for our purposes, just use Windows snipping tool to take a screenshot where you include the color bar. This isn't quite going to be good enough for publication. If you really want to publish one of these figures, we can talk about how to do this. But for the lab report, just taking a snapshot like this is going to be good enough. Alright, so now we've looked at the HOMO and LUMO of this molecule. We've looked at the computed electron density. We've looked at the electrostatic potential computed on the density isosurface, which it clearly distinguishes the negatively charged pi system from the positively charged NH hydrogens. The last thing we're going to do is look at atomic partial charges. Now, the nice thing about Gaussian is that it computes atomic partial charges automatically in every calculation by default. But to see them, we have to go take a look at our log file. Now, if we're lucky, we can look at the log file, aniline.log. We can look at that in Gauss view. There we go. So here we can go up to the Results tab, look at charge distribution. So we have, well, for some reason, those were not reported. So there's an incompatibility issues, I'm not sure what, between this version of Gauss view and the newer version of Gaussian 16. So it's probably going to be best for us to look at the log file itself to get the computed charges. To do this, we want to go to View Labels. Each atom in a Gaussian calculation has a different number. This carbon's number 1, the nitrogen's number 12, the paracarbon's number 4, and so on. So what we're going to do is we're going to go to Explorer, the File Explorer, and we're going to go and open this log file. We're going to open it in Notepad. So this is the other text file that tells us all the things that that tells us all the things that we did from this geometry optimization. This is a long file. For example, if we look for the phrase SCF done, that shows us our total energy. There's our first total energy, minus 283/4.1325. You see the total energy as I look down and down the file is going lower and lower and lower, more and more negative as I get closer and closer to an optimized geometry. And now I found the end, and that would be the final energy that you would use in your computing energy differences, things like that from Module 2. But what we want is more towards the bottom. So the calculation is finished. There's our optimized geometry. There's our coordinates. These are the things we want. First, these numbers are the orbital energies. So the HOMO energy in this case is the highest energy of the occupied eigenvalues. It's minus 0.280 Hartree. So I could get ionization potentials and electron affinities approximately from these numbers. By default, Gaussian also does a population analysis, and the default method is called the Mulliken population analysis. So when you scroll down to the phrase Mulliken charges, those are your first set of computed charges. Just for keeping track of things, I'm going to copy and paste these numbers into an Excel spreadsheet. By doing so, I'm going to give you a better idea of what I mean when I say your supporting information should be all in Excel. So I'm going to minimize this a little bit, zoom in a little bit. Okay, and so I'm going to have 3 different columns. The first one's going to be the atom, 4 columns. First one's going to be the atom, its index, and its molecule charge, and its NPA natural charge. And I'm going to tell you later about what those mean. So, the first atom I'm going to look at is the substituted carbon, C1, which is index 1. The second atom I'm going to look at is nitrogen, which is atom number 12. And then the C meta, which could be either 5 or 3. We'll just look at 5. And then the para, C para. The para carbon is atom number 4, so it'll be number 4. Now I'm going to go take a look at the log file and say, all right, what are the molecule charges of those different atoms? Atom number 1 has molecule charge 0.390. Just copy and paste. The nitrogen, molecule charge minus 0.98. The metacarbon, number 5, is negatively charged. And the paracarbon is also a little more negatively charged. Just as an aside, if you really wanted to look at the chemistry of these, you might compare how do these charges differ from the charges of carbon in an unsubstituted benzene. But the last thing I want to show you today is that we can use a different method to get different atomic partial charges, and you need to look at trends in both different kinds to really make sense of it. So what we're going to do here is we're going to run one more Gaussian calculation. So we're going to start from the optimized geometry in aniline.log. We're going to set up a new calculation. We don't need to re-optimize, so this will just be an energy. And we're going to go to this tab NBO and say we're going to do NPA only. We're going to retain that. Now we're going to save this file. Aniline NPA. Now, again, we're going to run that calculation using the command line. So I'm going to go here, and in the command line, I'm going to go dir, double check that aniline NPA is there. I can dir star NPA star to look for all the files that have the letters NPA in them. Got just one. G116W, G16.exe, aniline NPA.gjf is going to be my input file. Aniline NPA.log is going to be my output file. I hit enter and I wait for a little bit while the calculation runs. This calculation recomputes the orbitals, recomputes the density, and does this natural population analysis. Now I can go back to my File Explorer and open the Documents folder, aniline NPA.log. Now I'm opening this again in Notepad, and I'm going to scroll down to the results of the natural population analysis. Blah, blah, blah. Here's the orientation of the molecule, the orbital energies again. You might want to double check that the orbital energies in this calculation match the orbital energies from the other calculation. Blah, blah, blah. Molecule charges, again, just an aside, our molecule charge of carbon 1 is the same as it was before. But down below that, we should have this natural atomic orbital and natural bond orbital analysis, this new thing. We look through that, and our results turn out to be natural atomic orbitals, a bunch of stuff that you don't really need to know about. Your result that you care about is summary of natural population analysis. The number you need is the natural charge. So carbon number 1, natural charge, 0.244. The nitrogen, atom number 12, the natural charge is minus 0.88. The metacarbon, carbon number 5, natural charge minus 0.9. The paracarbon, carbon number 4, natural charge minus 0.31. If I would really like to see this in a little more detail, I could visualize this with a column plot. This column is indexed. I don't need that. Just delete it. And there we go. I have the molecule and the natural charges of carbon 1, the nitrogen, and the meta and the paracarbons. You see that overall the trends are about the same, but the NPA gives relatively more negative charge on the paracarbon. The trends are the same, the absolute values are not. Neither of these results is quote-unquote right or correct. Remember, there's no single, unique, unambiguous way to assign partial charges to an atom and a molecule. However, the natural population analysis tends usually, not always, but usually to give results that are more in line with chemical intuition. So if you want to talk about partial charges in an atom or molecule, natural population analysis is a decent thing to try. So with that, I've shown you how to compute orbitals and look at them in real space. I've shown you how to compute densities and electrostatic potentials. I've shown you 2 different ways to compute atomic partial charges. And we've learned a lot about working from the command line, which is going to be the most reliable way to get Gauss View working. So with that, we will close this video.